Click the bell icon to get latest videos from Ekeeda.
Hello friends, today we will discuss the theory of functional dependencies and every aspect of it, whether being in a closure of a functional dependency of a relation to help it to decompose it in different type of normal forms and how to preserve the dependency while preventing the decompositions, how to actually perform the lossless decompositions. When we talk about functional dependency, that means the dependency of one attribute to other attribute or a part of the set of attributes so that we are uniquely defining a relation and no redundant information is being stored in the relation. So to move to the redundant information and the functional dependency of a relation, we must need to know what is the closure of a relation. Well, we can say that a closure of a relation is another relation which has been satisfying all the functional dependencies that were preserved in the original relation. So let us more look at the formal definition. Now we can say that is a relation R with the attributes A, B, C, G, H, I. Now when we talk about functional dependency, we can use the term alternatively that we are logically implied by. So if there is in a closure, that is we denote by giving the plus sign on the upper right. So the F plus is a closure of F, or we can say the R plus of R, if every logical implications of forming this attribute sets satisfies on F, also satisfied on F plus. So for our example, we are preserving the functional dependencies in F. Now if we look at this preservances or the dependencies on this, we can say that taking the first and the last one, that is A depending on B and B is dependent on H. So we can say that the relation A is a dependent of H is logically implied. So logically implied means that it is not recorded in the list of functional dependencies, but from the functional dependencies we can imply a particular another dependency. So the logical implications or a transitive dependency is a dependency which can be formed by any of the two or more dependencies from the existing functional dependencies. So for if there exists T1 for A which is equals to T2 for A. That means if there exists an attribute A for which the tuple values of T1 and T2 are same, so A implies B means that there exists T2 that is matched with all the values of B of T1. Now this one exists and say that T1 of H will be matched with T2 of H. That means the logical implications we have termed it as a tuple relational. So the tuple relational say that every attribute on T1 and T2, if there is an imply sign, then the second right will also match for this one. So we can say that directly T1 and T2 for A and H are same. That means then A and H implications is satisfied. So this is the logical implications on a functional dependency, and that we can also take as a part of the closure F plus. That means the closure F plus of F have all the functional dependencies as well as the logical implication dependencies deserving from the functional dependencies. Now we will talk about axioms. Axioms are rules that we take into account, or the Greek letter notations that we take into account for having a preservation of functional dependency, or to more correctly define the functional dependency. Now we'll take the Armstrong's axioms that the scientist Armstrong has provided some rule to define those dependencies and closure of a relation. We will look at this very first. So the reflexibility axiom or rule. So the first rule states that if there is an alpha attribute or a set of attributes and beta belongs to alpha, then we can say that for every beta that belongs to alpha, it satisfies the alpha implies beta. That means if beta is a part of alpha, then obviously alpha can define the beta. That means if there is a department ID combination, then the ID or the department can individually imply the department or thus as a part of the alpha or the set of rules. Next is the augmentation rule. So if there is a functional dependency alpha implies beta and we can say that gamma are the set of attributes, then also we can say that gamma alpha belongs to gamma beta holds for that relation. So that we are augmenting alpha from beta to gamma alpha to gamma beta. That if there is CGH, that means also CH and GH. So we can derive it like this way. So that is known as an augmentation admission. Next is the transitivity rule. The transitivity axiom states that if there exist two dependencies, alpha defines beta and beta defines gamma, then we can say that alpha defines gamma holds for the relation. Now, till now that we have known that the Armstrong's axioms are all sound because they do not produce any incorrect values, and they are also complete because all the closure that can build on the relation F can have generated from the F or can be added to it. Next comes with the union. If we can say that there exists alpha belongs to beta and also we can say that alpha defines gamma, then we can mention that alpha defines beta gamma holds. That means we are actually unioning two of the defining relation. See, the left-hand side must match with each other, not the right-hand side. If the left-hand side is different and the right-hand side is same, then the union rule will not hold. Next, the reverse of the union rule, that is a decomposition rule. So it states that if there exists an alpha belongs to beta gamma, then we can say that alpha belongs to beta and alpha defines gamma holds. That means if there is a combination of set or attributes that a single attribute is defining, so we can separately say that the attribute is defining each of the attributes separately. If there exists an alpha belongs to beta or alpha defines beta, we can pseudo transitivity apply to it. Then we can apply another attribute gamma to each of the part of the transitivity to make it as a single result alpha defines beta. How to do that? Say that pseudo attribute is gamma here. So we can say so the gamma beta defines delta and alpha gamma defines delta. That means gamma beta is defining delta. First alpha gamma is defining delta and from that delta we can have the gamma beta. That is why the transitivity alpha defines beta we can gain from this pseudo transitive rules. Now let us apply the Armstrong's axioms in our example where we had the functional dependencies on a set of attributes A, C, G, H, I. Now we have already shown that how to transitivity rule apply into the functional dependency to have a logical implication on a closure of F, that is F plus. Now let's look at this. We know that in our example we had CGH and CG defines I. So we can put the union axiom here and we can generate in our closure that CG defines HI as an application of the union rule. Now let us apply the pseudo transitivity rule. As we have A implies C and also CG implies I. So applying the pseudo transitivity rule that G is a part of combination on a C, but C is actually defined by A. So we can say that A defines I as a pseudo transitivity. Now we can also apply the augmentation rule so that A defines C, we can say that AG defines CG as the augmentation and also CG defines I. So we can have AG defines I or we can say A defines I. So we can have it as a pseudo transitivity or as a part of the augmentation and transitivity. So that are the applications of the axioms of Armstrong into our example or in any relation. So now we can have 3 or 4 more than the functional dependencies on a relation F in the closure F plus. Now these are all for the functional dependencies. Now how to make the closure of an attribute set of a relation F? If I want to put the closure of an attribute set, then we must satisfy first the functional dependencies and then we can add it to our closure that the values that being a part of the functional dependencies. Let us see by a repeat statement or the logic block by how we can add the attributes in the closure of F plus of a relation F. Obviously, as the relation F has got the attributes and F plus has that attribute plus more attributes that can be generated by the combination of attributes on the functional dependencies, then it will be large as well as expensive. But it will also help us to serve our queries in a database or in making a normal form. That is why we look for the closures. So to make the F plus on attributes of F, we need to perform the following algorithm. So first we need to do the functional dependency adding. Now we are putting the algorithm first for each functional dependency F in the closure F plus, we need to apply the reflexibility rule as well as the augmentation rule in F to has the representation on the closure F plus. Now after applications to the reflexibility and augmentation rule, we need to add the result in the F plus. Now if there exist two functional dependencies F1 and F2 in F plus, so that we can combine the F1 and F2 by transitivity, then add the result to the F plus. Now we need to repeat this sentence until and unless the F plus does not change for any other F. So that is the algorithm for adding the functional dependencies in a relational closure. Now we will put the relational closure under the attribute alpha. So now we are putting the alpha in our closure F plus. Now for each functional dependency that is beta defines gamma in F, we need to perform the following loop. So if B belongs to the result, that means result has got alpha in it. So if B belongs to this result, that B is a part of the result for the functional dependency that beta defines gamma, that means alpha also defines gamma. So we can add the result with this gamma union as a gamma attribute to the set of result. And we need to perform it until and unless we has the result set of attributes starts from alpha, then beta, gamma and all other attributes. So in this way we can add the attributes in our closure F plus. Now let us perform this algorithm in the particular example that we have taken. Say for example we are making a closure of a combination of key AG. So our closure of AG plus, that is, will contain all the combinations of AG. So in AG we can have, now that we have this one, A belongs to B. So in F that it is the A defining B. So that our result is considering AG. So our result set now belongs with AG. As it supports that A belongs to B in F, then we can just add B as the gamma part to the result. So now my result has A, B, C, G. Now let us perform this one. CG defines H. So as we have C, A and both G as the result set in this ABCG, so CG define H, that means H will be added up and union with this attribute set. So now my result set become A, B, C, G, H. So we have started from AG, then we have added B. Next from the dependency AC, we have added C. Now from CG defines H, we have added H. We have one more. See, now we have also I getting unioned into the result set because CG defines I. Now we have all the attributes that we have started, and from the AG plus closure we cannot have any more further attribute added to it. So it is the final attribute result set and our iteration will stop because the result will not change further because we cannot add any more attributes to it. So that is the algorithm performed and we can have the closure of an attribute. Now, where to use these algorithms or where to use the closure of attributes? So there are many key areas where we can use them. First is to test the primary key. If I want to test that alpha is a primary key or not, we just compute that alpha plus or the closure of alpha. If the closure of alpha contains all the keys that were present in alpha, then we can easily say that alpha is the primary key of that particular relation. Now to check that a functional dependency holds or not. If a functional dependency we are checking it is holding to a schema or not, we generally constitute a beta belongs to alpha. Next we check that beta belongs to alpha plus or not. If it belongs to alpha plus, that means we have all the relations or the attributes of alpha in this one. So alpha defines beta will definitely satisfy. So for the functional dependency holding, for the primary key checking. Now we can also create the attribute closure of a closure to actually calculate the closure of the relation. That means to calculate the functional dependencies. If we can say so if there is a gamma that belongs to R and the S that belongs to the R plus or the gamma plus, then we can definitely say that gamma defines S. That means we are adding a functional dependency to the closure to check it as an attribute closure dependency exists or not. Now we will talk about the canonical cover. We can calculate the canonical cover, but for that we need to know about how to do and where to do the canonical cover. There are some situations where we got some attributes that can be deleted from the data as a part of the redundant information without changing the exact composition of a functional dependency attribute. So that attributes are known as extraneous attributes. So extraneous attributes are attributes we are actually an extra attributes to the functional dependencies or the closure of the dependencies, which will not deleted and make effect in the closure changing of the dependency. So if we delete the extraneous attributes from our relation, then we can compute the canonical cover very easily. So canonical cover is a cover for which that will include all the functional dependency at its minimum or can give the degree of the relation. So first we have A as an extraneous attribute if A belongs to A and also belongs to small a in such a way so that we can calculate that F subtracted from the functional dependency alpha defines beta. That means we do not have any alpha defines beta in the relation F. And now if it is joined with alpha minus a, that is a belongs to the alpha, now we am subtracting alpha from a and now that defines beta. That means we are actually joining and logically implying F to B in such a way that it is defined by alpha attribute or a. So that is becoming that a as an extraneous attribute. There is one more way of defining the extraneous attribute. Now if we have an attribute A in beta and also A belongs to beta, then we can say if the set of functional dependencies that alpha belongs to beta subtracted from F, so we do not have any alpha beta in F, getting joined with all the related that have beta but not A and that is defined by alpha logically implies F. So here F logically implies the beta part and now this one logically implies F. So if this two attribution completion is there, then we can say that A is an extraneous attribute that we can delete to make it in a canonical cover. For our example, if there is a functional dependency AB defines T. Now we also have, so we can say that A defines C is already enough for this definition. So B is an extraneous attribute here. Now in another example, so we can say that C becomes an extraneous attribute here because A is already having defined this D. So AB D is more than enough to define the relation, where C is the extraneous. Now we will compute the canonical cover by removing all the extraneous attributes from the relation F and to make it as a canonical cover of F. First, we are taking F as the canonical cover of F, that is Fc. Now we will perform the loop to actually compute the Fc. So first we should use the union to remove and replace the functional dependencies in Fc of the form that is alpha defines beta 1, alpha defines beta 2. We can replace it to alpha defines b1 and b2 by removing these ones. So I am performing the first step of removing the extraneous attributes from the relation that has happened in the functional dependencies. Now we look for the functional dependencies alpha belongs to beta, for there exists an extraneous attribute A in either alpha or beta or both. Now we need to remove such extraneous attributes. Now after that it is removed from this attribute Fc, so we will continue till Fc doesn't change. That means Fc will have the minimum number of functional dependencies that will not contain any extraneous attribute. Now that the subtraction from F, the alpha defines beta, as well as the alpha subtracted from beta defines A, will definitely solve and hold for the relation Fc now, because it does not hold any of the extraneous attributes here. Now for our example for considering the canonical cover, if we look at the example at definitely C is an extraneous attribute, so we need to remove it. So after removing, we will get the result. So we can say that the canonical cover of F has F dash with AB defines B, A defines E, and E defines C. See, in the canonical cover, we are not putting any type of transitive dependencies or make a transitive rule applications. We are only deleting the extraneous attributes. So now we can more formally define the extraneous attributes and based on it the canonical cover. So the two portions that we need to consider, that there should be no functional dependencies that consist of an A or an extraneous attribute, or we can say if there exists a functional dependency, then the left hand side must always be unique. So we can say that in Fc, if there is two dependencies, alpha 1 belongs to b1 and alpha 2 defines b2, then alpha 1 cannot be equals to alpha 2. That means the unique left hand side or the defining attribute in the canonical cover. So that is all for canonical cover. Next we will move to our next part. Now let us get back to an example and first compute the canonical cover to compute it and use it as the next part of our discussion, which will consider it as the dependency decomposition. Now as we can see clearly that two of these dependencies first has the same attributes, that is A defines B. So the canonical cover condition says that we cannot have the same left hand sides functional dependencies. So the dependencies A defines BC and A defines B cannot exist together in Fc. Now we can say that A is extraneous in ABC and BC because we can have B implies C from this relation. So A is extraneous here. First we can combine it to A defines BC. So now we have A as the extraneous attribute as it repeated and also as a part of the B defines C relation. So we can prove it by using So this assertion is true because we do not have anything else, that is it will logically imply all the F's because AB defines C, then we can have only left with this B defines C, which I am unioning it, that means we are having all the relations in F. So this logically implies F and A is an extraneous attribute. Now C is an extraneous attribute in this one. It is logically implied by both A defines B and A defines C from AB defines C. So we can say that C is extraneous here, so we should remove it. So now in our canonical cover of FC we have A defines B from this relation as well as A defines C from this relation. So now our canonical cover consists of two of the dependencies and we cannot make anything lesser than this one. That means all the functional dependencies are preserved as well as we can have no extraneous attribute. Now we can say that canonical cover has not got any unique solution. We will see an example where we can define two of the canonical covers from the same set of relation F. Let us select this example. Now, if we look at this example that A defines BC and B defines AC, so A and B both becomes extraneous in this F. So we cannot delete just both because we will lose up our functional dependency preservation, which we cannot do in the canonical cover. So to perform the canonical cover, we need to find the extraneous attributes, delete any one of them and then perform. And that leads to the duplicity, or we can say that the loss of uniqueness in the canonical cover. If we start with the deletion of A, it will result in another canonical cover than if we start with B. Let us perform all this. Now if we delete C from this extraneous attribute because it repeats there and there both. So now we will result in Now B is not an extraneous attribute anymore because we have deleted C. So we cannot just delete B and C both. Now if we look at this, then from the part of this C defines AB, we can look that A and B both are extraneous. So what should we do? Now first, as A and B both are extraneous, we try to remove B from it. If we try to remove B from it, we will result in C defines A. And now as a result, as A is being extraneous, we will have B defines C. Now let's look at this. There is one more canonical cover possible. If we define and delete A from here, so we result in C defines B. So now the B defines AC, both are not extraneous. So B defines AC is also a part of this canonical cover. So of a single deletion of T13 with this F relation, we have two canonical covers. Now there are more possibilities if we start with the deletion of B. So if B is deleted, then we have the F dash as Now there also we can have the A and B duplicacy in there or an extraneous, so we will result in the similar canonical covers like the previous one. So first I will start with A defines C. For that, in this relation A becomes extraneous, so C defines B, and for this one again we have C becomes extraneous, so B defines A. Now for the second one, if we start with deleting A from it as an extraneous, so B defines C, and now A, B not become an extraneous because they are all different, not the same on the left side. So it will be defining C defines AB. So there are more possibility of having greater than 2, 3, 4 canonical covers from a single relation F. Now that we have computed the canonical cover and know about the extraneous attribute, we will perform the lossless decomposition. In lossless decomposition, we will decompose our relation into 2 or more subparts so that when we will join them, we will not lose any of the data on that relation, or we will not have an erroneous data that can occur in the relation. Now that we have decomposed our relational attributes R from the relation R into 2 parts, that is R1 and R2. So if we put the SQL query like select all the tables from R1 from R and R2 from smaller, naturally joining them. So the lossless decomposition suggests that all the data that were preserved in R are also presented in this resultant small r as a combination of an R1, R2. So what is a lossy decomposition? A lossy decomposition makes any logical data loss or physical data loss in the resultant relation R if it is not a lossless. So we must say that in a lossless decomposition, R1 intersection R2 to define this R1 as well as R1 intersection R2 will define R2. We can say that it will be a lossless decomposition. For our example, let us take at the relations. Now if we divide this into 2 of the relations, and now we can have only the instructor. So the R1 intersection R2 is the department which defines the ID, name and salary as well as the building and budget. So we can say that this decomposition is a lossless decomposition. Now what happens if I try to find out that the customer relation into 2 parts? Let's look at this. Now I am dividing it into 2 parts, that is considering the ID name and the name city. Now if I made an intersection of R1 and R2, I will have name. Well, name cannot uniquely define C1 because the name can be repeated for a customer. There can be 2 or more customer name of the same name. That is a Kim being the name of 3 or more customers. So we cannot define the names on C1 and C2, as we will lose the data if we decompose it in this way. So when we will join it, we have an ID, name, city, but not in the previous manner that was preserved here. So now if there is an ID name, say suppose 501 Kim and 502 Kim. Now as the C2 will have Kim, Delhi, Kim, Mumbai. So my combination or the natural join will have 501 Kim, Delhi, 501 Kim, Mumbai, 502 Kim, Delhi, 502 Kim, Mumbai. Now we have lost our data that which Kim, that 501 is representing Delhi or 502 is representing Mumbai or not. So we have all the possible combinations but not the result that which Kim is residing in which city. So that is considered to be a lossy decomposition. So the lossy decomposition cannot the common attribute name uniquely define each of the relations, and the combination will have an erroneous data. Now that we know about the lossless decomposition, we should know the last one, that is the dependency preservation. How to preserve a dependency in a relation. So now we will talk about the decomposition in dependency preserving. So when we are composing the data and decomposing it into two smaller schemas, then we need to consider the dependency preserving. Let us look at this example. Now that our attribute set is A, B and C, we are decomposing it into two parts that has got AB and AC. Now that the relation AC, which has A defines C, which is not present in the dependency of this A. So if we calculate the F plus and also the closure of F dash plus, that is the resultant decomposed closure. So if these two matches, that means all the relational dependent preservancies is present in the closure of the decomposed data, then we can say that the decomposition was dependency preserving. So if these two matches with each other, then the decomposition is in dependency preserving. Let us perform an algorithm to reach the dependency preservation in decomposition. Now first we need to compute the closure F plus so that we can have all the combination of the dependencies in the closure and to check against the closure to make it a decomposed closure. So first we are matching this Ri, that means R1, R2 to Rn. In D, that is the resultant set. So we are repeating this. First, for every Fi, we are computing all the restriction of this F plus in Ri. That means if there is any dependency that is matching or that is missing from Ri. Now we are making the F dash into null. That means we are clearing all the closure or the repeatant set on the relation. So there are no more dependencies that we are attaching it to this dependent preserved. For now that we have made this one as null, that we will compute and add every dependency to it. That is, we are calculating the closure of the decomposed relation. Now we are adding the restrictions that we have in Ri into the F dash. That means all the dependencies that is preserved in F dash or this composed of the Ri, we are adding it to the closure of F dash. Now that we have calculated the closure of the decomposed relation. So if these two matches, then the result will be true. That means that is a dependency preserving decomposition. Other than false, that means the preservation is not there. So that is to compute and check that dependency preservation is there or not. But it is very expensive and large to compute the closure of the decomposed relation. So is there any other way to check for the dependency preserving other than calculating the closure of that relation? Yes, we can also compute and check for the dependency preservation in decomposition without calculating the closure. Here we will use the attribute set to achieve and check the preservation. See, for every Ri, we are calculating the result that is consisting the attribute set alpha, and now we are intersecting with the Ri, taking its closure so that we can have all the attributes in the closure of the attributes, not the relation. Now we are again intersecting with the final Ri, so that we can have only the attributes that were present in Ri but not present in this closure. So first idea was calculating the closure to check the functional dependency present in the decomposed closure or the functional dependency, and the second is to calculate the attribute set that is present in this closure but not in the actual set, so that the dependencies is being preserved. That means if the intersection has got all the attributes that belongs to the dependency or the functional dependency, then we can uniquely say that the dependency is preserved in the decomposition. So in this way we can provide and check for the dependency preservation in decomposition, as well as we can also look for the lossless decomposition. So thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda.